Repeat again. And copy the right triangle PXQ in a new page, and we will implement the Pythagoras theorem on this right triangle PXQ. So actually, this is the right length triangle PXQ that I copied from the original drawing. In this right triangle PXQ, according to the Pythagoras theorem, PQ squared, that is the square of the hypotenuse, equals to PX squared plus XQ squared. So I write it down. PQ squared, that is the square of the hypotenuse, must be equal to PX squared plus XQ squared. PQ is 11, therefore PQ squared is 11 squared, that is 121, and it is equal to PX squared. PX is the missing side, so we leave it as it is, plus XQ squared. XQ is 5, therefore XQ squared is 5 squared, that is 25. So in total, we found out that 121 equals to PX squared plus 25. Here we subtract 25 from this equation, and finally get it 121 minus 25 is 96, equals to PX squared. 96 is 16 times 6, so we substitute 96 by 16 times 6, so 16 times 6 equals to PX squared. Here we take a root out of this equation, and finally get that the missing side Px is equal to the square root of 16 times 6. The square root of 16 is 4, so inside the root we left only with 6. So in total we actually found out that the length of the missing line segment Px is equal to 4 times square root of 6 units, 4 times square root of 6 units. This is the missing side Px, is equal to 4 times square root of 6 units in its length. We have already found out that AES XP is a rectangle, and the opposite sides of a rectangle are equal to each other. So in rectangle AES XP, side PX must be equal to the opposite side AES. Again, side PX must be equal to the opposite side AES. But PX is 4 times square root of 6, therefore the opposite side AS must be also equal to 4 times square root of 6 units in its length. We'll join points P, and we define the point of tendency of tangent EH with this small circle. This point is point Y, and we'll join points P and Y together by a straight line. PY is of course the radius of this circle, that is equal to 5. Y is the point of tendency of tangent EH with this small circle. So according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So in this small quadrilateral EA YP, we have 1, 2, 3 angles, and therefore this fourth missing angle must be also equal to 90 degrees in its size. So inside the small quadrilateral EAYP, we have 4 angles, and therefore can relate to quadrilateral EAYP as a rectangle, but we know that the opposite sides of a rectangle are equal to each other. So in rectangle EAYP, side YP must be equal to the opposite side EA. But YP is 5, therefore the opposite side EA must be also equal to 5 units in its length. In the next step, we will join the center of this medium circle, that is point Q, this is point Q, with the center of this big circle, that is point S. We'll join points Q and S together by a straight line. According to Rule 10, the straight line that connects the centers together of the medium circle and the big circle, that is the straight line QS, this is straight line QS, must pass through their touching points. This is their touching point. We define their touching point. This point is point M. According to Rule 10, the straight line QS that joins their centers together must pass through point M, that is their touching point. It is very clear that those two circles have an external notch between them at point M. Therefore, can definitely implement Rule 10. So, the straight line QS that connects their centers together must pass through point M, that is their touching point. That is to say, QMS is one straight line. QMS is one straight line. QM is the radius of this medium circle. That is equal to 6 units in its length, according to what is given in the question. SM is the radius of this big circle. That is equal to 8 units in its length. And because of the fact that QMS is one straight line, it means that QS equals to QM plus MS. So QS equals to QM, that is 6 plus MS, that is 8. That is to say, QS equals to 6 plus 8, that is 14. QS equals to 14 units in its length. It's actually the distance between the centers of this medium circle and this big circle. In the next step, from point Q, that is the center of this medium circle, we will draw perpendicular on CT. Again, from point Q, we will draw perpendicular on CT. CT is a straight line. According to what we already found out, the CT is a straight line. So from point Q, we draw perpendicular on the straight line CT. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point Q in the straight line CT. This point is point H. When doing this construction, we can do the right triangle SQH. The hypotenuse of this right triangle SQH is SQ, that is equals to 14 units in its length. What is the length of this short line segment SH? In order to find out the length of this short line segment SH, we must focus on this quadrangle QHTB. Inside this quadrangle QHTB, we have 1, 2, 3 right angles. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside this quadrangle QHTB, we have 4 right angles. According to Rule 5, this quadrangle must be this rectangle if not a square, so relate to this quadrangle QHTB as a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in this rectangle QSTB, side QB must be equal to the opposite side HT. But QB is 6, therefore the opposite side ST must be also equal to 6 units in its length. Now it is very easy to find out the length of this short line segment SH. SH equals to ST minus HT. Again, ST minus HT equals to SH. So already now, SH equals to ST minus HT. So SH equals to ST is 8, it is the radius of the big circle, minus HT. We just right now found out that HT equals to 6. HT equals to 6. So SH equals to 8 minus 6, that is 2. HT equals to 2 units in its length. Now we implement the Pythagoras law on this green triangle SQH. So I copy the green triangle SQH in a new page and we will implement on it the Pythagoras theorem. Here by PT is the evaluation for Pythagoras theorem. So actually this is the right green triangle QSH that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle QHS, SQ squared, that is the square of the hypotenuse, equals to SH squared plus HQ squared. So write it down. SQ squared, that is the square of the hypotenuse, is equal to SH squared plus QH squared. SQ, the hypotenuse SQ equals to 14 units in its length. Therefore, SQ squared is 14 squared, that is 196, and it is equal to SH squared. SH is 2, therefore SH squared is 2 squared, that is 4, plus QH squared. QH is the missing side, so we leave it as it is. So it is plus QH squared. In total, we found out that 196 equals to 4 plus QH squared. Here we subtract 4 from this equation and we get that 196 minus 4 is 192 equals to QH squared. 192 is 64 times 3. So we substitute 192 by 64 times 3 equals to QH squared. Here we take a root out of this equation and finally get that QH equals to the square root of 64 is 8. So inside the root we left only with 3. So it is 8 times root of 3 units in its length. So we found out that the missing line segment QH equals to 8 times root of 3 units in its length. This is the missing line segment QH, this is equal to 8 times root of 3 units in its length. So this is quadrilateral QHCS. Inside this quadrilateral QHCS, we have 1, 2, 1, 2, And actually here we have EF is a straight line because it is one side of the big rectangle. If we focus on the straight line EF at point S, the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side at the lower side of EF at point S? We have this angle, this is a right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So inside quadrangle CSQH, we have 1, 2, 3 right angles, and therefore this fourth missing angle must be also equal to 90 degrees in its size. So inside quadrangle CSQH, we have 4 right angles. Therefore, according to rule 5, it is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle SCHQ, side QH must be equal to the opposite side SC. But QH is 8 times square root of 3. Therefore, the opposite side SC must be also equal to 8 times square root of 3 units in its length. We actually found out the value of the length of rectangle EFQH. The length EF is EA plus AS plus SC plus CF. And the area of a rectangle equals to the length of the rectangle times the width. The width is 16 and the length is the sum of those 4 numbers. And that is the answer to the question. The multiplication of 16 by the sum of those 4 numbers will give us the area of this rectangle EFHQ. So already now we should find out that the area of rectangle EFHQ is equal to the width times the length. The area of rectangle EFHQ equals to the width of the rectangle times the length. The width is EH. And the length is EF. The length is EF. The width EH equals to 16 units in its length. The width equals to 16 units in its length. And the length EF equals to EA plus AS plus SC plus CF. So in total, we have found out that the length of the big rectangle EFHQ equals to 16 times EA plus AS plus SC plus CF. So in total, it is equals to 16 times EA. EA is 5 plus AS. AS is 4 times square root of 6 plus SC. SC is 8 times square root of 3 plus CF. CF is 8. So in total, we should find out that the area of rectangle EFHQ is equal to 16 times 5 plus 4 times square root of 6 plus 8 times square root of 3 plus 8. The value of this expression in total is equal to 586 0.47 square units in its size. So the answer to the question is that the area of this big rectangle EFHQ is equal to 586.47 square units in its size. So we finish with the first question. In the next step, I will present to you the second question and solve the second question by using two different methods. In the second question, our task is to find out the area of this circle. So in the drawing, we have a circle. This is called PQ, that is equal to 6 units in its length. This is called AB, that is equal to 8 units in its length. This is angle PMQ, that is a right angle. Again, our task is to find out the area of this circle. In order to find out the area of this circle, so we start of course with the first method. In order to find out the area of this circle, I will present to you Rule 29 and we will implement Rule 29 in our drawing. According to Rule 29, peripheral angles that subtend on the same arc are equal to each other. So in the drawing we have a circle. This is peripheral angle BAQ. This is equal to alpha according to our definition. Peripheral angle BAQ subtend on arc BC. Again, peripheral angle BAQ subtend on this green arc BC. Likewise, this is peripheral angle CEB. This is equal to beta degrees in its size according to our definition. And peripheral angle CEB subtend on the same arc BC. And because of the fact that those two peripheral angles subtend on the same arc, they must be equal to each other in their sizes. This is to say peripheral angle BDC is equal to peripheral angle BEC, or alpha equals to beta. So repeat again, according to Rule 29, if two peripheral angles subtend on the same arc, they must be equal to each other in their sizes. In this case, angle alpha must be equal to angle beta. So we can actually implement Rule 29 in our drawing. Why? Because if we focus on this arc BQ, this is arc BQ in the red line, and peripheral angle BAQ subtend on arc BQ. Again, peripheral angle BAQ subtend on the red arc BQ. Likewise, this is peripheral angle MPQ, this is peripheral angle BPQ, this is peripheral angle BPQ that subtend on the same red arc BQ. And according to Rule 29, because of the fact that those two peripheral angles subtend on the same arc, they must be equal to each other in their sizes. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other according to Rule 29. Likewise, we'll focus on this black arc AP. This is arc AP in the black color. And again, this is arc AP, and this is peripheral angle AQP that subtend on arc AP. Again, peripheral angle AQP subtend on arc AP. Likewise, this is peripheral angle APB that subtend on the same arc, arc AP. And because of the fact that those two peripheral angles subtend on the same arc, they must be equal to each other in their sizes. So if we define the size of this angle as beta, then the size of this angle must be also equal to beta because they are equal to each other according to rule 29. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. But this angle equals to 90 degrees, and therefore this angle must be also equal to each other. This angle must be also equal to 90 degrees in its size because they are equal to each other. This is the right triangle ABM. This right triangle ABM, the sum of the angles must be equal to 180 degrees. That is to say, in the right triangle ABM, the sum of the angles must be equal to 180 degrees. So which angles we have in this right triangle ABM? This is angle alpha, plus this angle beta, plus this angle that is 90 degrees. In total, they must be equal to 180 degrees, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. Here we'll subtract 90 degrees from this equation, and we get that alpha plus beta equals to 180 degrees minus 90 degrees is 90 degrees. So alpha plus beta equals to 90 degrees. Here we will multiply this equation by 2, and we get that 2 alpha plus 2 beta equals to 2 times 90 degrees is 180 degrees. So 2 alpha plus 2 beta equals to 180 degrees. In the next step, I'll present to you rule 13, and we'll implement rule 13 in our drawing. According to rule 13, a central angle is twice as large as the peripheral angle subtended on the same chord. In the drawing, we have a circle. This is peripheral angle ACB. The size of this peripheral angle ACB is theta. This is central angle and angle peripheral angle ACB subtend on chord AB. Again, peripheral angle ACB subtend on chord AB. Likewise, this is central angle AOB that subtend on the same chord called AB. And according to this rule 13, the size of this central angle AOB must be twice as large as the size of the peripheral angle that subtend on the same chord. So peripheral angle AOB subtend on chord AB. The size of peripheral angle AOB is theta, and therefore central angle AOB that subtend on the same chord called AB must be twice as large as this angle. That is to say, it must be equal to theta. So according to this rule 13, the size of the peripheral angle is twice as large. The size of the central angle is twice as large as the size of the peripheral angle that is subtended on the same chord. So in the next step, we will create two peripheral angles. We define the center of this circle. This point is point O. We will create central angle AOP. This is central angle AOP that subtend on arc AP. Again, central angle AOP subtend on arc AP. Likewise, peripheral angle AQP, this is peripheral angle AQP, that subset on the same arc RKP. According to rule 13, the size of this center angle must be twice as large as the size of this peripheral angle that subset on the same arc RKP. So the size of this peripheral angle AQB is beta, therefore the size of the center angle must be equal to 2 beta, according to rule 13. Likewise, we get another center angle. So okay, this is center angle BOQ that subtend on arc BQ. Again, center angle BOQ subtend on arc BQ. Likewise, peripheral angle BAQ subtend on the same arc BQ. Again, peripheral angle BAQ subtend on the same arc BQ. And according to rule 13, the size of this center angle BAQ must be twice as large as the size of this peripheral angle ABQ, because both of them subtend on the same arc RPQ. The size of this peripheral angle ABQ is alpha, therefore the size of center angle BMQ that is also subtend on the same arc BQ must be equal to 2 alpha. Actually, this is peripheral angle B, center angle BOQ that is equals to 2 alpha. Repeat again. This is center angle BOQ. The vertex of any center angle must be the center of the circle, that is point O. So this is center angle BOQ. The size of center angle BQ must be twice as large as the size of this peripheral angle BAQ that subset on the same arc BQ. So the size of peripheral angle BQ is alpha, therefore the size of center angle BOQ must be equal to 2 alpha. In the next step, we'll define angle QOP. This angle SX, and we define this angle AOB, this angle SY. We have the rule that says that the sum of the angles around any point is equal to 360 degrees. Again, we have the rule that says that the sum of the angles around any point is equal to 360 degrees. So the sum of the angles around point O must be equal to 360 degrees. So which angles we have around point O? We have 2 beta plus x plus y plus 2 alpha. Or 2 beta, 2 alpha plus 2 beta. Which angles we have around point O? We have 2 alpha plus 2 beta plus x plus y. In total, the sum of those 4 angles, they must be equal to 360 degrees. But we have already found out that 2 alpha plus 2 beta equals 280 degrees. Therefore, we substitute 2 alpha plus 2 beta here by 180 degrees plus x plus y is equals to 360 degrees. Here we'll subtract 180 degrees from this equation, and we get that x plus y equals to 360 degrees minus 180 degrees is 180 degrees. So again, we found out that x plus y equals to 180 degrees. In the next step, I will present to you rule 30, and we will implement rule 30 in our drawing. According to rule 30, central angles that subtend on equal chords are equal to each other. Again, central angles that subtend on equal chords are equal to each other. In the drawing, we have a circle. This is central angle COD. This is equal to alpha degrees inside. This is central angle AOB. This is equal to beta degrees inside. Central angle COD subtend on arc CD, central angle AOD subtend on arc AB. And according to this rule 30, if chord CD equals to chord AB, then those two central angles must be equal to each other in their sizes. That is to say, alpha equals to beta. Again, if chord CD equals to chord AB, then the sizes of those two angles must be equal to each other. That is to say, alpha equals to beta. Okay, again, according to rule 30, central angles that subtend on equal arcs must be equal to each other in their sizes. So we can actually implement rule 30 in our drawing. This is the central angle QOP. The size of central angle QOP is x degrees, and central angle QOP subtend on chord PQ is equals to 6 units in its length. Again, central angle QOP subtend on chord PQ is equals to 6 units in its length. So I will draw this circle again, and we create an angle, central angle with chord that is equal to 6 units in its length, and according to rule 30, the central angle must be equal to central angle QOP. Why? Because they have equal chords. Okay, so I'll draw this circle again. Actually, the circle is with the same radius, is exactly the same circle. Point O is the center of the circle. I will draw chord AB. Actually, I will draw this center angle AOB. This is equal to y degrees in its size. This is called AB, with the chord from the original drawing. This is third triangle AOB. This is equal to y degrees in its size. Third triangle AOB subtend on on chord AB. Now from point B, I will draw chord. The length of the chord will be 6 units, and this way I'll create a center angle that will be equal to x degrees in its size. Why? Because it will have exactly a chord. It will subtend on chord that is equal to 6 units in its length. So the new chord that I will draw will create center angle that is equal to x degrees in its size, because the length of the chord will be equal to 6 degrees, exactly like this chord PQ. And according to rule 30, center angles that subtend on equal chords must be equal to each other in their sizes. So I will draw chord BC is equal to 6 units in its length according to our construction. Again, this is chord BC that is equal to 6 units in its length according to our construction. In the next step, I'll join points O and C together by certain point O is the center of the circle. So we have here center angle BOC that subtend on chord BC that is equal to 6 units in its length. According to rule 30, center angles that subtend on equal chords are equal to each other. This is center angle QOP that subtend on chord PQ that is equal to 6 units in its length. So those two center angles are equal to each other in their sizes because they both subtend on equal chords. This is center angle QP that subtend on chord QP that is equal to 6 units in its length. This is chord BO. This is center angle POC that subtend on chord BC that is also equal to 6 units in its length. And therefore, the size of this center angle must be equal to the size of this center angle because they both subtend on equal chords, 6 and 6. The size of this center angle POQ is x, and therefore the size of this center angle BOC that subtend on equal chords with 6 units must be also equal to 6 degrees in its size according to rule 30. Again, center angle BOC equals to center angle BOC equals to center angle QOP because they both subtend on equal chords, 6 and 6. The size of this center angle is x, therefore the size of this center angle that subtend on equal chords that is equal to 6 units must be also equal to x degrees in its size. We have already found out that x plus y equals to 180 degrees. Again, x plus y equals to 180 degrees. This is angle AOC. The size of angle AOC is x plus y. That is to say, the size of angle AOC is 180 degrees because x plus y equals to 180 degrees. And we know that any angle that is equal to 180 degrees in its size, it is defined as a straight line. Therefore, AOC is a straight line, and therefore AC is a straight line. Again, AC is a straight line because angle AOC equals to 180 degrees in its size. AC is a straight line. But AC is a straight line that touches the circle at 2 points, A and C. Therefore, AC is a chord. AC is a chord that passes through point O, that is the center of the circle. And we know that any chord that passes through the center of the circle is defined as a diameter. Therefore, AC is the diameter of this circle because AC passes through point O, that is the center. It is a chord that passes through the center of the circle, that is point O. So AC is the diameter of the circle. So as you know, AC is the diameter of the circle. Here we can implement rule 7. I repeat quickly on rule 7, and we'll implement rule 7 in our drawing. According to rule 7, if a peripheral angle subtends on the diameter of the circle, then it must be equal to 90 degrees. In the drawing we have a circle. This is peripheral angle ACB that subtends on the diameter of the circle, that is AB. Again, peripheral angle ACB subtends on AB, that is the diameter of the circle, and therefore according to this rule, rule 7, peripheral angle ACB must be equal to 90 degrees in its side. Why? Because it subtends on the diameter of the circle. So according to rule 7, any peripheral angle that subtends on the diameter of the circle must be equal to 90 degrees in its size. You can definitely implement rule 7 in our drawing. Why? Because in our drawing we have peripheral angle ABC that subtends on AC, that is the diameter of the circle, and therefore according to rule 7, peripheral angle ABC must be equal to 90 degrees in its size. So in the next step, we'll implement the Pythagoras theorem on this right triangle ABC. So it is given us the question that AB equals to 8 units in its length. AB equals to 8. BC equals to 6 units in its length according to our construction. And AC is the diameter of the circle. So in the next step, I will copy the right triangle ABC in a new page and we will implement on it the Pythagoras theorem. Here by PT is the progression for Pythagoras theorem. Actually, this is the right triangle ABC that I put this moment. This right triangle ABC, according to the Pythagoras theorem, AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. So already now, AC squared, that is the square of the hypotenuse, is equal to AB squared plus BC squared. AC is the missing side, so we leave it as it is. So it is AC squared, that is equal to AB squared. AB is 8, therefore AB squared is 8 squared, that is 64, plus BC squared. BC is 6, therefore BC squared is 6 squared, that is 36. So in total we found out that AC squared equals to 64 plus 36, that is 100. AC squared equals to 100. Here we take a root out of this equation and finally get that AC equals to the square root of 100, that is 10. So if we found out that the diameter of this circle is equal to 10 units, so the radius R must be equal to AC over 2, that is 10 over 2, that is 5. So the radius R of the circle equals to 5 units. Our task is to find out the area of this circle. Actually, we know that the area of any circle equals to pi times the radius of the circle squared. Repeat again, the area of any circle equals to pi times the radius of the circle squared. And therefore, the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle squared is r squared. So the area of our circle must be equal to pi r squared. But r is 5, therefore r squared is 5 squared, that is 25. So in total, the area of our circle must be equal to 25 pi square units in size. So in terms of numbers, it is equal to 78.54 square units in size. But again, if we found out that the area of this circle is equal to either 25 pi square units in size, or in terms of numbers, the area of this circle is equal to 78.54 square units in size. So we finish with the first method. In the next step, I will present to you how to find out the area of this circle according to the second method. We already found out in the first method that those two angles are both equal to alpha. So I'll not repeat on the same explanation. Those are vertex angles that are equal to each other. This angle is 90 degrees, and therefore this angle must be also equal to 90 degrees in its side. So in the right triangle AMQ, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first BC angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in any triangle. Likewise, in this right triangle PMQ, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first BC angle must be equal to 90 degrees minus alpha, according to the same rule that the sum of the angles in any triangle is equal to 180 degrees. PQ is a chord in this circle. PQ is a chord, it is absolutely a straight line. So if you focus on the right side of the straight line PQ at point M, here the sum of the angles must be equal to 180 degrees according to all three. All three states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the right side of the straight line PQ at point M? We have this angle that is the right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to all three. Therefore, this missing angle must be equal to 90 degrees in its size. Those two right triangles are similar to each other according to angle similarity rule. This is to say those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So if you found out that all the figures of this right triangle PMQ are correspondingly equal to all those triangles in the right triangle AMQ. And therefore those two right triangles are similar to each other according to angle similarity rule. So it is done if you found out that the right big triangle PMQ is similar, this is the sign of similar, to the right triangle AMQ according to angle similarity rule. And from the fact that those two triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AQ of the right triangle AMQ over side PQ of the right triangle PMQ is equal to side AM of the right triangle AMQ over side PQ over side PM of the right triangle PMQ, and it is also equals to side MQ of the right triangle AMQ over side actually we have 2 points in the same name. So here, this is triangle AMQ and this is triangle PM. Check it. Actually, this is point B. And this is point Q. Okay. So I'm picking again from the fact that those two right triangles are similar to each other, the following relationship exists between their sides. So triangle A and B is similar to triangle PMQ according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AB of the right triangle ABM or side PQ of the right triangle PMQ is equal to side MB of the right triangle AMB or side MQ of the right triangle MPQ. It is also equal to side AM of the right triangle AMB. So it is equal also to side AM of the right triangle AMB or side PM of the right triangle PMQ. And again, from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AB of the right triangle AMB or side PQ of the right triangle PMQ is equal to side MB of the right triangle AMB or side MQ of the right triangle PMQ, and it is also equal to side AM of the right triangle AMB or side PQ of the right triangle PMQ. AB is 8 over PQ. PQ is 6, and it is equal to MB over MQ, and it is also equal to AM over PM. So in total we should find out that 8 over 6 equals to MB over MQ equals to AM over PM. Here we divide both the numerator and the denominator of this number by 2. 8 over 2 is 4, 6 over 2 is 3. It is equals to AM over PM. So two sides are equal to each other. So 4 over 3 equals to AM over PM. Here we multiply both the numerator and the denominator of this number by A. We get the 4A over 3A equals to AM over PM. Those two sides of the equation are equal to each other. That is to say, the numerator of this side is equal to the numerator of this side. That is to say, AM equals to 4A. Likewise, because of the fact that those two sides of the equation are equal to each other, it means that the denominator of this side must be equal to the denominator of this side. That is to say, PM equals to 3A. So we should find out that AM equals to 4A and PM equals to 3A. This is side AM, that is equals to 4A. This is side PM, that is equal to 3A. Those two sides of the equation are also equal to each other. That is to say, four thirds is equal to MB over MQ. Again, 4/3 equals to MB over MQ. Here we will multiply both the numerator and the denominator of this number by B. Actually, B over B is 1, and therefore it is allowable to multiply any expression by 1 will not change the value of the expression by multiplied by 1, and therefore it is allowable to do the operation. Again, the remote of this side must be equal to the remote of this side of the equation. That is to say, mb equals to 4b. The remote of this side of the equation must be equal to the remote of this side of the equation. That is to say, 3b equals to mq, or mq equals to 3b. So mb equals to 4b and mq equals to 3b. mb equals to 4b. This is side mb. That is equals to 4b. This is side mq. That is equals to 3b. In the next step, we'll join points B and Q together by a straight line. By joining points B and Q, we're going to do the right triangle MBQ. So I'll copy the right triangle MBQ in a new page, and we'll implement on this right triangle MBQ the Pythagoras theorem. MB equals to 4B units in its length. MQ equals to 3B units in its length. And the hypotenuse BQ is the missing side, so we leave it as it is. Here by PT is the proportion for Pythagoras theorem. So here, this is the right triangle MBQ. This again equals to 90 degrees in its size. According to all three. So this is the right triangle MBQ, the document from the original drawing. This right triangle MBQ, BQ squared, that is the square of the hypotenuse, equals to BM squared plus QM squared. So write it down. BQ squared, that is the square of the hypotenuse, is equal to PM squared plus QM squared. BQ is the missing side, so we leave it as it is. So it is BQ squared equals to BM squared. BM is 4B, therefore BM squared is 4B squared, that is 16B squared, plus QM squared. QM is 3B, therefore QM squared is 3B squared. So in total, if you found out that BQ squared equals to 16B squared plus 3B squared. 3B squared is 9B squared. Plus 16B squared equals to BQ squared. So in total, BQ squared equals to 16b squared plus 9b squared is 25b squared. So bq squared equals to 25b squared. Here we take a root out of this equation and find that bq equals to the square root of 25 is 5 and the square root of b squared is b. So in total we should find out that the length of the hypotenuse bq is 5b units. So here this is the hypotenuse bq that is equals to 5 units in its length. The hypotenuse bq equals to 5 units in its length. In the next step, we'll calculate the area of this triangle AQB in two different ways, and we create a new equation that states that the area of the triangle AQB according to the first method must be equal to the area of triangle AQB according to the second method. We know that the area of any triangle equals to the base of the triangle times the height to the base over 2. Therefore, the area of this triangle AQB will be equal, we take the base as AQ times the height to the base. The height to the base is MB because it's greater than 90 degrees with the base AQ. The height is MB divided by 2. So according to the first method, we actually found out that the area of triangle AQB equals to the base AQ times the height MB over 2. In the next step, we calculate the area of triangle AQB in a different way. Here we have triangle ABC that could be any triangle. Side AB equals to A unit in its length. Side AC equals to B unit in its length. Side BC equals to C unit in its length. This is angle CAB. The size of angle CAB is theta. And according to the new formula, the area of triangle ABC that could be any triangle equals to A times B times sinus theta over 2. Again, the area of this triangle ABC equals to A times B. That is the multiplication of two sides with each other times sinus the angle that is between the two sides. That is sinus theta. Again, times sinus the angle between those two sides. This is angle theta. Here, I'll read again, the area of the triangle ABC equals to A times B times sinus theta over 2. So, we use the new formula in order to find out the area of this triangle ABQ. According to the new formula, the area of triangle ABQ will be equal to AB times BQ times sinus, the angle between the two sides, that's the angle ABQ. Divided by 2. If it again, the area of triangle ABQ according to the second method is equal to AB times BQ. This is the multiplication of two sides by each other times sinus the angle between the two sides, AB and BQ. The angle between the two sides is angle ABQ. Again, the angle between side AB and side BQ is angle ABQ. So it is sinus angle ABQ over 2. So the area of triangle ABQ according to the first calculation must be equal to the area of triangle ABQ according to the second calculation. Here we have 2 both sides of this equation, so 2 will get cancelled. We have to find out what is the value of sinus angle ABQ. This is the value of sinus angle ABQ. In order to find out the value of sinus angle ABQ, we implement the law of sines in this triangle ABQ. Triangle ABQ is blocked by this circle. So we use the law of sines in order to find out the value of sinus angle ABQ. So according to the law of sines, this is triangle ABC that could be any triangle. Side AB equals to C units in its length, side AC equals to B units in its length, side BC equals to A units in its length. This is angle alpha, this is angle beta, and this is angle gamma. And the circle that blocks this triangle ABC, the radius of the circle that blocks this triangle ABC is defined as R. So according to the law of sines, the following equation is true. That A over sinus alpha equals to B over sinus beta equals to C over sinus gamma, that is equal to 2R. And 2R is the diameter of the circle that blocks this triangle ABC. We can definitely implement the law of sines in our drawing, because in our drawing we have triangle ABQ, a triangle ABC could be any triangle. Triangle ABQ is blocked by this circle, and the radius of this circle is R. So by implementing the law of sines in this drawing, we'll find out the radius of this circle, and the area will be equal to the radius squared times pi. Okay, so first of all, we'll find out the value of sinus angle ABQ by implementing the law of sines in this triangle ABQ. According to the law of sines in this triangle ABQ, AQ over sinus this angle, this is actually over sinus of the angle that is in front of AQ. So it is AQ over sinus ABQ is equal to 2R. And 2R is the diameter of this circle that blocks triangle ABQ. So according to the law of sines, if we implement the law of sines in our drawing on triangle ABQ that is blocked by this circle, we get that AQ over sinus ABQ is equal to 2R, and 2R is the diameter of this circle that blocks this triangle ABQ. So we should find out that according to the law of sines, AQ over sinus angle ABQ equals to 2R. So we will multiply this equation by sinus ABQ, and then we divide it by R in order to find out the value of sinus ABQ. Repeat again. We will multiply this equation by sinus ABQ, and then we divide it by 2R. In this way, we will find out the value of sinus ABQ. And we get that AQ over 2R equals to sinus ABQ. And again, we multiply this equation by sinus angle ABQ and then we divide it by 2R. In this way, we actually found out that AQ over 2R equals to sinus angle ABQ. Now we can substitute sinus angle ABQ by AQ over 2R. We do it now and we get that AQ times MB equals to AB times BQ times sinus angle ABQ. And sinus angle ABQ equals to AQ over 2R. R is the radius of the circle that blocks triangle ABQ. Here we have AQ on both sides of this equation, so AQ will get cancelled. After cancelled AQ, in this side of the equation we left only with MB. So MB equals to AB times BQ over 2R. Here we will multiply this equation by R and we divide it by MB in order to get the value of R, that is the radius of the circle, and we get that R equals to AB times BQ over 2 times MB. Repeat again. We divided this equation by MB and we multiplied by R simultaneously and found out actually that the radius R, that is the radius of the circle that we were looking for, is equal to AB times BQ over 2 times MB. So R equals to AB is 8 times BQ. BQ is 5B. Over 2 times MB. MB is 4B. So it is over 2 times 4B. So in total we found out that R equals to 8 times 5B over 2 times 4B. We have 8 in the denominator and 2 times 4 is 8. So we have 8 in the denominator and 8 in the denominator, so 8 will get cancelled. B over B is 1. So in total we found out that the radius R of the circle is equal to 5 units. Our task is to find out the area of this circle. Actually, we know that the area of any circle is equal to pi times the radius of the circle squared. Therefore, the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle squared is r squared. So the area of our circle must be equal to pi r squared. But r is 5, therefore r squared is 5 squared, that is 25. So in total we found out that the area of our circle is equal to 25 pi square units in its size. In terms of numbers, it is equal to 78.54 square units in its size. Repeat again, in both methods, we found out that the area of this circle is equal to either 25 pi square units in its size, or in terms of numbers, the area of this circle is equal to 78.54 square units in its size. So we finished to answer the second question. The next step, as far as the lecture, we'll start with the first question, of course. In the first question, our test was to find out the of this big rectangle EFQH. So in the drawing we have a rectangle. Inside this rectangle we have 3 circles. The radius of this small circle is equal to 5 units in length. The radius of this medium circle is equal to 6 units in length. And the radius of this big circle is equal to 8 units in length. Again, our test is to find out the area of this big rectangle EFQH. So first of all, we know that all the angles inside any rectangle are right angles. So those 4 angles are all right angles. Here we can implement rule 1 in our drawing. According to rule 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. For example, we have here the radius QB is equal to x. The radius QB is drawn to point B, that is the point of tendency of tangent HQ with this circle. And whenever we have a radius that is drawn to the point of tendency, then tangent HQ will be perpendicular to the radius BQ. If HQ is perpendicular to BQ, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 1. Likewise, those two angles also equals to 90 degrees according to rule 1. Those two angles are equal to 90 degrees, both those two angles. Those two angles, according to the same rule, they are both equal to 90 degrees. And those two angles are both equal to 90 degrees according to rule 1. Okay. So we have here in this quadrilateral CFLS, we have 1, 2, 3 angles. Therefore, this fourth missing angle must be equal to 90 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So inside quadrilateral CFLS we have 4 angles. Therefore, we can relate to quadrilateral CFLS as a rectangle, but we also know that the opposite sides of a rectangle are equal to each other. So in rectangle CFLS, side SL must be equal to the opposite side CF. But SL is 8, therefore the opposite side CF must be also equal to 8 units in its length. Likewise, the lower quadrilateral SLQT, we have 1, 2, 3 angles, and therefore this fourth missing angle must be equal to 90 degrees in its size. So this is angle CST. Angle CST equals to 180 degrees. Again, angle CST equals to 180 degrees, and therefore line segment CST is the straight line, or line segment CT is a straight line. CT is a straight line, and therefore shape ACTH is a quadrilateral because it has 4 sides. 1, 2, 3, 4. In this quadrilateral ECTH, we have 4 right angles. 1, 2, 3, 4. And therefore we can relate to this quadrilateral CSTH as a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in the big rectangle ECTH, side CT must be equal to the opposite side EH. But CT in total is 8 plus 8, that is 16. Therefore the opposite side EH must be also equal to 16 units in its length. So if we found out that the width of this rectangle EFQH is equal to 16 units. So here we did a construction. This is to say we extended the radius BQ by a straight line until it touches side EF of the rectangle, and we define the touching point of the extended line segment BQ with side EF of the rectangle. This point is point S. By doing this construction, we can do quadrilateral ESBH. Inside quadrilateral ESBH, we have 1, 2, 2 3 rectangles. Therefore, this focus area must be equal to 90 degrees in its size. So inside quadrilateral ESBH, we have 4 rectangles, and therefore quadrilateral ESBH is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle ESBH, side EH must be equal to the opposite side SB. But EH is 16, therefore SB must be also equal to 16 units in its length. Again, this is side SB. This is equals to 16 units in its length. In the next step, we did the construction. That is to say, from this point P, we do perpendicular on BS. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point P and SB. This point is point X. By doing this construction, we get there from the other ESXY. Inside this quadrilateral ESXY, we have 1, 2, 3, 4 right angles. Therefore, quadrilateral ESXY is a rectangle. No, actually, from point 3 we do perpendicular on SB, so this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. By doing this construction, we get there quadrilateral AESXP. Inside quadrilateral AESXP, we have 1, 2, 3 rectangles. Therefore, this fourth angle must be equal to 90 degrees in its size. Therefore, quadrilateral AESXP is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle AESXP, side AS must be equal, side AP must be equal to the opposite side SX. But AP is 5, therefore the opposite side SX must be equal to 5 units in its length. We know that QB is the radius of this medium circle. This is equal to 6 units in its length. So what is the length of this line segment XQ? XQ equals to SB minus SX minus QB. And again, XQ equals to SB minus SX minus QB. So XQ equals to SB, that is 16, minus QB, that is 6, minus SX, that is 5. So total QX equals to 16 minus 5 minus 6, that is 5. This is the missing side XQ. This is equal to 5 units in its length. In the next step, we join points P and Q together by straight line. The big circle have an external edge with this medium circle and this point Z. That is to say, they touch each other externally at point Z. Therefore, we can implement the rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects their centers together. What is the straight line that connects their centers together? The center of this circle is at point P. The center of this circle is at point Q. The straight line that connects their centers together is of course the straight line PQ. And according to rule 10, the straight line PQ must pass for point Z, that is their touching point. Or PZQ is one straight line. PZQ is one straight line according to rule 10. If PZQ is one straight line, it means that PQ equals to PZ plus ZQ. PZ is the radius of this small circle, that is 5. ZQ is the radius of this medium circle, that is 6. So in total, PQ must be equal to 5 plus 6, that is 11. So PQ equals to 11 units in its length. XQ equals to 5. So in the next step, I copied this green rectangle PXQ and implemented the pattern on this green rectangle PXQ. according to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendicular. So this is the right triangle PXQ, and the limit from the original domain. According to the Pythagoras theorem, PQ squared, that is the square of the hypotenuse, equals to PX squared plus XQ squared. PQ is 11, therefore PQ squared is 11 squared, that is 121, and it is equals to PX squared. PX is the missing sign, so it is, plus XQ squared. XQ is 5, therefore XQ squared is 5 squared, that is 25. So in total, we should find out that 121 equals to PX squared plus 25. Here we subtract 25 from this equation, and we found out that 121 minus 25 is 96, so 96 equals to px squared. Here we substituted 96 by 16 times 6, and we took out of this equation, and we found out that px, the missing side px, is equal to the square root of 16 times 6. The square root of 16 is 4, so inside the root we left only with 6. So in total we found out that px, this is 97px, that is equal to 4 times square root of 6 units in its length. We already found out that the quadrilateral ASXP is a rectangle, and we know that the opposite sides of the rectangle are equal to each other. So in the rectangle ASXP, side px must be equal to the opposite side AS, but px is 4 times square root of 6, therefore the opposite side AS must be equal to 4 times square root of 6 units in its length. Likewise, we join points Q and S together by straight line. Point Q is the center of this medium circle, point S is the center of this big circle. So QS is a straight line that connects the centers together, and according to rule 10, the straight line QS must pass through point M, that is their touching point, or QMS is one straight line. QMS is one straight line. If QMS is one straight line, it means that QS in total equals to QM plus MS. So QS equals to QM, that is the radius of this medium circle, that is 6, plus MS, that is the radius of this big circle, that is 8. So in total, QS equals to 6 plus 8, that is 14. QS equals to 14 units in its length. In the next step, we did the construction, that is to say, from point Q, that is the center of this medium circle, we do perpendicular on CT. Again, from point Q, we do perpendicular on CT. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point Q and CT. This point is point H. By doing this construction, we get the right rectangle QSH. Therefore, QS equals to 14 units in its length. What is the length of the short line segment SH? SH equals to ST minus HT. Again, SH equals to ST minus HT. So SH equals to ST is 8, and HT is 6. So in total, SH equals to 8 minus 6, that is 2. So in the next step, we'll call it the right triangle QSH in the new page, and we implemented the Pythagoras theorem on this right triangle QSH. So this is again right triangle QSH, and they're going from the original domain, and this is right triangle QSH. QS squared, that is the square of the hypotenuse, must be equal to SH squared plus HQ squared. QS is 14, therefore QS squared is 14 squared, that is 196, and it is equal to SH squared. SH is 2, therefore SH squared is 2 squared, that is 4, plus HQ squared. HQ is the missing side, so it is. So total, if you found out that 196 is equal to 4 plus QS squared, here we subtracted 4 from this equation, if you found out that 196 minus 4 is 192 equals to QH squared. 192 is 46 times 3, so 64 times 3. So we should find out that 64 times 3 equals to HQ squared. Here we took out all the equation, and we found out that the square root of 64 is 8. So inside the root we left only 3. So in total we should find out that QH equals to 8 times square root of 3 units in its length. And again, this is line segment QH, QS. This is 97 QH. So the 97 QH. That is equals to H times square root of 3 units in its length. For the other SCHQ is a rectangle because it has 1, 2, 3, 4 right angles. And the opposite sides of a rectangle are equal to each other. So a rectangle SCHQ, side QH must be equal to the opposite side SC. But QH is 8 times square root of 3, therefore the opposite side SC must be also equal to 8 times square root of 3 units in its length. We already found out that CF equals to 8. So we know that the length of rectangle EFQH is EF, and EF in total equals to 5 plus 4 times square root of 6 plus 8 times square root of 3 plus 8. The length is this expression, the sum of those four numbers, and the width is EH, that is 16. The length times the width is this rectangle EFQH. Repeat again, the length of rectangle EFQH, that is the looking for this question, is equals to the width times the length. The width is EH, and the length is EF. EH is 16, and EF is EA plus AS plus SC plus CF. EH is 16, and EF is EA plus SA plus SC plus CF. So it is 16 times EA is 5, SA is 4 times square root of 6, SC is 8 times square root of 3, and CF is 8. So the multiplication of those two numbers by each other will give us 586.47. That is actually the area of this rectangle EFQH. Repeat again, we actually found out that the area of this rectangle EFQH is equal to 586.47 square units in its size. So finish with the first question. In the next step I presented to you the second question, and you solve the second question by using two different methods. Our task in the second question is to find out the area of this circle. So in the drawing we have a circle. This is called AB, this is equals to 8 units in its length. This is called PQ, this is equals to 6 units in its length. This is angle PMQ, that is a right angle. Again, our task is to find out the area of this circle. So, first of all, I presented to you all 29, and I presented all 29 in our drawing. According to all 29, peripheral angles that subset on the same arc are equal to each other. In the drawing we have a circle. This is peripheral angle BDC. This is equals to alpha, and peripheral angle BDC is subset on arc BC. Likewise, this is peripheral angle BEC that subset on the same arc BC. And because of the fact that those two peripheral angles subset on the same arc BC, they must be equal to each other in their sizes. That is to say, alpha equals to beta. So according to this rule, all 29 peripheral angles that subset on the same arc are equal to each other in their sizes. Okay. Implement all 29 in our drawing. In our drawing, we have, this is peripheral angle BAQ, peripheral angle BAQ that subset on arc BQ. Likewise, this is peripheral angle QPB that subset on the same arc BQ. And because of the fact that those two peripheral angles subset on the same arc BQ, they must be equal to each other in their sizes. So if the size of this angle is alpha, then the size of this angle must be equal to alpha according to rule 29. In the next step, we focus on this arc AP. We have this is perpendicular PQA that subtend on arc AP. Likewise, this is perpendicular ABP. This is also subtend on the same arc AP. Because of the fact that those two perpendiculars subtend on the same arc AP, they must be equal to each other in their sizes. So if the size of this angle is beta, then the size of this angle must be also equal to beta because they are equal to each other. Those two angles are defined as vertex angles. We know that vertex angles are equal to each other. But this angle equals to 90 degrees according to what is given as the equation. Therefore, this missing angle must be equal to 90 degrees in its size. So in the right triangle ABM, this angle equals to alpha, this angle equals to beta, and this angle equals to 90 degrees. And we know that the sum of the angles in any triangle must be equal to 180 degrees. So in the right triangle ABM, alpha plus beta plus 90 degrees must be equal to 180 degrees. Here we subtract 90 degrees from the equation and find that alpha plus beta equals to 180 degrees minus 90 degrees is 90 degrees. Here we multiply this equation by 2 and find that 2 alpha plus 2 beta equals to 180 degrees. And again, we found out that 2 alpha plus 2 beta equals to 180 degrees. In the next step, we get some triangle AOP that subtend on arc AP. And according to rule 13, the size of the third triangle is twice as large as the size of the peripheral that subtend on the same arc. Peripheral ABQ subtend on arc AP. Therefore, and it is equal to beta degrees in its size. And therefore, the size of third triangle AOP that subtend on the same arc AP must be equal to 2 beta. Likewise, here we can do peripheral BOQ that subtend on arc BQ. Peripheral BAQ also subtend on the same arc BQ, and it is equal to alpha. Therefore, the size of the third triangle BOQ must be equal to 2 alpha. It is twice as large of this peripheral that subtend on the same arc BQ. We define this angle POQ as x and this angle AOB is y. And we know that the sum of the angles around any point is equal to 360 degrees. I repeat again. The sum of the angles around any point is equal to 360 degrees. So, therefore, the sum of the angles around point O, that is the center of the circle, must be equal to 360 degrees. So, which angles we have around point O? We have 2 beta plus 2 alpha plus x plus y equals to 360 degrees. Repeat again, if you focus on point O, the sum on point O, the sum of the angles around point O must be equal to 360 degrees. So 2 alpha plus 2 beta plus x plus y must be equal to 360 degrees. But we already found out that 2 alpha plus 2 beta equals to 180 degrees. Therefore, we can substitute 2 alpha plus 2 beta here by 180 degrees, and we get that 180 degrees plus x plus y equals to 360 degrees. Here we subtracted 180 degrees from this equation, and we found out that x plus y equals to 360 degrees minus 180 degrees is 180 degrees. And again, x plus y equals to 180 degrees. In the next step, I presented to you rule 30 and implemented rule 30 in our drawing. According to rule 30, certain angles that subtend on equal chords are equal to each other. In the drawing we have a circle. This is certain angle COD. that is equal to alpha degrees in size, and is subset on chord CD. This is a triangle AOB that is equal to beta degrees in size, and it's subset on chord AB. And according to this rule 30, if chord CD equals to chord AB, then those two perpendiculars must be equal to each other in their sizes. Why? Because they subtend on equal chords. Again, if chord AB equals to chord CD, then those two, the size of those two perpendiculars must be equal to each other. Again, if AB equals to CD, then alpha equals to beta, according to rule 30. So, in the drawing we have center triangle AOB, this is equals to Y, and we have center triangle POQ, this is equals to X. So I draw this circle again, exactly the same circle, with center triangle AOB. This is exactly the same circle of the original drawing, and this is angle AOB. The size of angle, center angle AOB is y degrees, and it's subtended on chord AB. This is equal to 8 units in its size. This is center angle POQ. The size of center angle POQ is x, and it's subtended on chord PQ. That is equal to 6 units in its length. So actually, from point B, we draw chord BC in such a way that the length of chord BC will be equal to 6 units, exactly 6 units. Again, chord BC in such a way that the length of chord BC is equal to 6 units. And we join points O and C together by straight line. In this way, we get that center angle BOC is equal to 6 units. Center angle BOC is equal to x. Center angle BOC that's subset on chord BC that is equal to 6 units in its length. And because of the fact that those two center angles, they're both subtend on equal arcs. They're both subtend on arcs with length of 6 units. They must be equal to each other in their sizes. But the size of this angle is x, the size of this center angle POQ is x, therefore the size of this center angle BOC must be also equal to x degrees, because they both subtend on equal arcs. That is 6 units. According to rule 30, they must be equal to each other in their sizes. The size of this angle is x, therefore the size of this center angle must be also equal to x degrees, according to rule 30. So if we found out that the big angle AOC, in total it is equal to x plus y degrees in its size, but we already found out that x plus y equals to 180 degrees. Repeat again. We already found out that x plus y equals to 180 degrees. Here we have here we already found out that x plus y equals to 180 degrees. So the big angle AOC equals to 180 degrees, because x plus y equals to 180 degrees. And we know that any angle that is equal to 180 degrees in its size, it is defined as a straight line. Therefore, AC is a straight line. AC is a straight line because it is equal to 180 degrees in its size. And because angle AOC equals to 180 degrees in size, therefore AC must be a straight line. So AC is a straight line. But AC is a straight line that touches the circle at 2 points, A and C. Therefore, AC is a chord that passes from point O, that is the center of the circle, And we know that any chord that passes through the center of the circle must be the diameter of the circle. Therefore, chord AC that passes through the center of the circle must be the diameter of the circle. Again, AC is the diameter of the circle. Now we can implement rule 7 in our drawing. According to rule 7, if a peripheral angle is equal to 9, if a peripheral angle subtends on the diameter of the circle, it must be equal to 90 degrees in its size. This is peripheral angle ABC that subtends on the diameter of the circle, this is AC, therefore it must be equal to 90 degrees in its size. So peripheral angle ABC must be equal to 90 degrees in its size because it subtends on AC, that is the diameter of the circle. So triangle ABC is a right angle. So with the right triangle ABC in an equation, we implement the Pythagorean theorem on this right triangle, triangle ABC. So actually, this is the right triangle ABC that according to the original drawing, side BC equals to 6 units in itself according to our construction. Side AB equals to 8 units in itself according to what is given as a question, that we have already found out that AC is the diameter of the circle. According to the Pythagorean theorem, AC squared, that is the square of the hypotenuse, must be equal to AB squared plus BC squared. AC is the BC side, so we have the CT, so it is AC squared equals to AB squared. AB is 8, therefore AB squared is 8 squared, that is 64, plus BC squared. BC is 6, therefore BC squared is 6 squared, that is 36. So in total we should find out that AC squared equals to 64 plus 36, that is 100. So AC squared equals to 100. If we took out of this equation, we find out that AC, that is the diameter of the circle, is equal to 10 units in its length. If the diameter AC is 10, then the radius is 5. So the radius of this circle is equal to 5 units in its length. Our task is to find out the area of this circle. We know that the area of any circle is equal to pi times the radius of this circle squared. And therefore the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle squared is r squared. So the area of our circle must be equal to pi r squared. But r is 5, therefore r squared is 5 squared, that is 25. So in total we should find out that the area of this circle, that is the area that we are looking for in this question, it is equal to either 25 pi square units in size, so in terms of numbers it is equal to 78.54 square units in size. So we finish with the first method. In the next step I presented to you how to find out the area of this circle according to the second method. In the second method, we use some of the things that we already found out in the first method. We have already found out that those two angles are both equal to alpha. Those two angles are vertex angles that are equal to each other. So they are both equal to 90 degrees. So in the right triangle A and B, this angle equals to alpha. This angle equals to 90 degrees, and therefore this missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, this right triangle PMQ, this angle equals to alpha, this angle equals to 90 degrees, and therefore this missing angle must be equal to 90 degrees minus alpha. According to the sum rule, the sum of the angles in any triangle is equal to 180 degrees. It is very easy to see that those two right angles are similar to each other according to angle similarity rule. That is to say, both those two angles are equal to alpha, therefore they are equal to each other. Likewise, both those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So if you found out that all the angles of this right triangle A and B, of course, will be equal to these angles of the right triangle P and Q, therefore those two right angles are similar to each other according to angle similarity rule. And again, if you found out that the right triangle A and B is similar, this is the sum of similar to the right triangle P and Q according to angle similarity rule. And from the fact that they are similar to each other, we derive that the following relationship exists between their sides. We derive that side AB of the right triangle A and B over side PQ of the right triangle PMQ is equal to side MB of the right triangle PMB over side MQ of the right triangle PMQ, and it is equal to side AM of the right triangle AMB or side PM of the right triangle PMQ. Hit again. From the fact that those two right triangles are similar to each other, we realize that the following relationship exists between their sides. That AB over PQ equals to MB over MQ equals to AM over PM. AB is 8, PQ is 6. 8 over 6 is 4/3. If we divide both the numerator and the denominator by 2, we get that 8 over 6 is 4/3, and it is equal to AM over PM. We multiply both the numerator and the denominator of this number by A. We found out that 4A over 3A equals to AM over PM. Those two sides of the equation are equal to each other. Therefore, the numerator of this side of the equation must be equal to the numerator of this side of the equation, that is to say, AM equals to 4A, and the denominator of this side of the equation must be equal to the denominator of this side of the equation, that is to say, PM equals to 3A. So, AM equals to 4A and PM equals to 3A. This is side AM, this is equals to 4A, and side PM equals to 3A. Likewise, those two sides are also equal to each other. That is to say, 4/3 equals to MB over MQ. 4/3 equals to MB over MQ. We multiply both the numerator and the denominator of this number by B. It is allowable to multiply anything by 1. B times B over B is 1. So it doesn't change the value of the expression. So the numerator of this expression, of this side of the equation, must be equal to the numerator of this side of the equation. So MB must be equal to 4B, and QM must be equal to 3B. MB equals to 4B, and QM equals to 3B. In the next step, we join points B and Q together by a straight line. Actually, code PB, as a code, it is absolutely a straight line. So if you focus on the right side of the straight line PB at point M, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at the right side of the straight line PB at point M? We have this angle that is 90 degrees, plus this missing angle, in total must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. And therefore, we have here the right triangle PMQ. I copied this right triangle BMQ in a new page and we implemented the Badalos theorem on this right triangle BMQ. This is the right triangle BMQ that I copied from the original domain. According to the Pythagoras theorem, in this right triangle BMQ, BQ squared, that is the square of the hypotenuse, equals to BM squared plus MQ squared. BQ is the missing side, so we leave it as it is, so BQ squared equals to BM squared. BM is 4B, therefore BM squared is 4B squared, that is 16B squared plus MQ squared. MQ is 3B, therefore MQ squared is 3B squared. So BQ squared equals to 16B squared and 3B squared is 9B squared. So BQ squared equals to 16B squared plus 9B squared. 16B squared plus 9B squared is 25B squared. So in total, we found out that BQ squared equals to 25B squared. Here we took out all of this equation and we found out that BQ equals to the square root of 25, that is 5, over square root of B squared, that is B. So in total, we found out that BQ equals to 5B units in its length. This is side BQ, this is equals to 5B units in its length. In the next step, we calculated the area of this triangle ABQ in two different ways. And then we created an equation that says the value of the area of triangle ABQ according to the first method must be equal to the area of triangle ABQ according to the second method. The area of this triangle ABQ according to the first method of calculation is equal to the base AQ times the height of the base, that is MB over 2. Again, the area of this triangle ABQ according to the first method, it is equal to the base AQ times the I to the base MB over 2. And it must be equal to the triangle ABQ according to the second method. In the second method, we calculated the area of triangle ABQ in a different way. The area of triangle ABQ equals to AB times BQ times sinus angle ABQ over 2. And again, according to the second method, the area of triangle ABQ equals to AB times BQ times sinus angle ABQ over 2. Here we have 2 on both sides of the equation, so 2 will get cancelled. Here we implemented the law of cosines, the law of sines in our drawing in order to find out the value of sinus ABQ. According to the law of cosines, this is true in any triangle. This is triangle ABC that could be any triangle. In this triangle ABC, side AB equals to C unit in itself, side AC equals to B unit in itself, and side BC equals to A unit in itself. This is angle alpha, this is angle beta, this is angle gamma. So according to the law of cosines, according to the law of sines, in this triangle ABC that could be any triangle, the following equation is true. That A over sinus alpha equals to B over sinus beta equals to C over sinus gamma equals to 2R. And 2R is the diameter of the circle that blocks this triangle ABC. Again, 2R is the diameter of the circle that blocks triangle ABC. So we can implement the law of sines in our drawing. Why? Because in our drawing we have triangle ABQ, and we can implement the law of sines in any triangle. And we have triangle ABQ that is blocked by this circle. Therefore, we can definitely implement the law of sines in our drawing. According to the law of sines, the following equation will be true, that AQ over sinus angle ABQ equals to 2R. And 2R is the diameter of this circle. Again, AQ over sinus ABQ, that is the sinus of the angle in front of AQ, is equals to 2R. Again, AQ over sinus ABQ equals to 2R. Again, according to the law of sines, the following equation will be true, that AQ over sinus angle ABQ equals to 2R. And 2R is the diameter of this circle that blocks triangle ABQ. Here we multiplied this equation by sinus angle ABQ, and then we divided by 2R in order to find out the value of sinus angle ABQ, and we found out the 3. That sinus angle ABQ equals to AQ over 2R. Now we can substitute sinus ABQ in this equation by AQ over 2R. We did it, and we have found out that AQ times MB equals to AB times BQ, and sinus angle ABQ is AQ over 2R. Here we have AQ on both sides of the equation, so AQ will get cancelled. So in this side of the equation we left only with MB. This is equals to AB times BQ over 2R. Here we multiplied this equation by R, and we divided by MB simultaneously in order to find out the value of R. And we found out that R equals to AB times BQ over 2MB. AB is 8, BQ, again AB is 8, BQ is 5B, and QM is 3B. Again, AB is 8, BQ is 5B, and MB is 4B. MB is 4B. So here we have 8 in the numerator. In the denominator we have 2 times 4, that is 8, so 8 will be cancelled, and we have B over B, that is 1. So we left only with 5, so R equals to 5 units in its length. The radius of this circle, R equals to 5 units. Our task is to find out the area of this circle. Actually we know that the area of any circle equals to pi times the radius of the circle squared. Therefore, the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle squared is r squared. So in total, the area of our circle must be equal to pi r squared. But r is 5, therefore r squared is 5 squared, that is 25. Therefore, in total, the area of our circle must be equal to 25 pi square units in size. So in terms of numbers, it must be equal to 78.54 square units in size. So in both methods, we should find out that the area of this circle equals to either 25 pi square units in size. So in terms of numbers, the area of this circle equals to 78.54 square units in size. Okay, thank you very much.